Hello everybody, we're going to talk about related rates today. Related rates problems. And what are we trying to find in a related rates problem? Well, related rates, what we're trying to do is that we're trying to find the rate at which one quantity is changing by relating it to another quantity whose rates of change are known. And the way I like to think about this is like, when you've got one of these cute little kids' toys, kind of like this one over there with the little beads on the wires. And I remember when my son would be playing with these ones and seeing little kids playing with them, and I'd be thinking to myself, well, look, as we take one of these beads and move them along the wire, what happens? So if I had a wire that was shaped like this graph, y equals f of x right here, and I say, well, okay, if we're moving at some steady rate as x changes from left to right, look at what happens to the y value, right? It changes, but maybe it doesn't change quite as much. There are two different rates going on right here, and we know that the rate, as we move from left to right, we might say, well, that's a steady rate if that's moving from left to right at a steady rate. So we could say, well, the derivative of x, the change in the x value with the change in time. Let me let me make this something a little bit more alike to what we've been doing right here, right? We say, well, okay, if we're changing from x1 and we're going over to position x2 right here, we might say, well, there's some change in x. And if we were interested in the rate, we take that change in x over a change in time, and we look at that, and then we say, well, what about the change in y, right? We could say, well, there's a change in y here as well, right? We go from y1 to y2 over some change in time, and we would see that there's a change in rate, a change in time, and these two have to be related. Now, what we do that's a little bit more calculusy than this is we say, well, all right, let's look at it at a specific point then. At a specific point, right, if we let the two values get closer and closer to each other in value, what's going to happen? Well, at this particular point right here, we might find that, well, if x is moving at a specific rate, we could say, well, there's a specific instantaneous rate of change in x, and that should be an x, not a y. There should be an instantaneous change in the rate of x divided by an instantaneous change in time, right? And there could be related to that at this particular point a related change in y with respect to time. And so we call dy dt the change in the y values, and we call dx dt the change, instantaneous change in the x values. And we might be interested in finding the relationship between those rates. So that's what we're actually doing here in this particular section. And as an example, let's go with one that I actually do know. This is the curve y equals 4x cubed plus 2x squared. Here's what it looks like. And we're saying that, all right, we've got this point that's moving along. And it's moving along in such a way that dx dt, the rate of change in x for any point, is always a nice constant 1/2 of a unit per second. And we're interested in finding out what would be the rate of change of the y at the point where we're at the point 240 in this curve. So what do? Well, in this case, we're going to use something like the implicit differentiation model that we used before. We've got this relationship between x and y, and so what we would say is that, well, it would be useful if we could just take the derivative of both sides with respect to time, assuming that x and y are both implicitly functions of time here. And that's exactly what we do. We say, well, all right, if I take the derivative with respect to time of y on the left, it would be equal to the derivative with respect to time of the expression 4x cubed plus 2x squared on the right. So how do we handle that? Well, on the left, this is just simply saying, all right, the rate of change of y, the instantaneous rate of change of y with respect to time t is dy dt. On the right, we have to use something like a chain rule, right? We're going to have 4 times the derivative with respect to time of the quantity x cubed plus 2 times the derivative with respect to time t of the quantity x squared. Right? Now, t and x, they don't match right here. So what we're going to have to do is we're going to have to use our chain rule. And so we would find that dy dt is equal to 4 times the derivative of x cubed, which we know is 3x squared, times the derivative of x with respect to time. Right? So it's x as a function of t, so we have to multiply by dx dt at the end right here. And similarly, for the next piece, we would take the derivative with respect to time, t, and get 2x to the first times the derivative of x with respect to time. Okay, so as we work this out, we find that, well, dy dt would be equal to 12x squared plus 4x times the derivative of x with respect to time. All right, so if we're interested in the exact rate at which y changes with respect to time, and we know what dx dt is, right? We're given that dx dt is 1/2 of a unit per second. What do? Well, we can make our substitution. We can say that the derivative of y, the rate of change of y with respect to time, is going to be equal to, let's make our substitution, 12 times 2 squared plus 4 times 2 times dx dt, and we know that's equal to 1/2. All right, doing a little bit of work right here. This is 12 times 4, 48, plus 4 times 2, 8. So 48 plus 8 is going to give us 56. And 56 times 1/2, everybody, at the same time, you can tell me. 56 divided by 2, yes, that's 28 units per second. Now compare that. You could try this out and say, well, what would happen at, say, the 1 second mark or the 0 second mark, right? See what your rate of change of y is at each of these, and you would find that for each of them, that rate might be a little bit different. And it would make sense that as x is moving along steadily, that value, that rate of change of y is changing with respect to time. But in this case, at this particular point, it has to be 28 units per second.